Uh, Hello, folks. Welcome back to HCM5220 stats for healthcare management. Uh, as we begin kind of this journey into statistics, I always find it useful to know why a particular process or a particular procedure or a particular branch of knowledge evolved. And statistics evolved as a response to some changes in the way that we do science that occurred in the 19th century. And we'll talk about that a bit more later. But it was built on statistical processes, and the concept of statistics was built on a couple of ideas that were well known in the 19th century and prior to that. And one was the notion of normality, random and normality. And the other one is the notion of error, measurement error in particular. And since these things were fairly well known, they kind of laid the groundwork for how statistics evolved as a way of answering questions about primarily quantitative data. And so we knew some things, as I said, we knew some things going into the 19th century, and we need to understand what those things were. And so I'm going to probably, in the most simplest way I can, try to kind of talk about those using some images and some things from the web page. And so first, I want to talk about normality and random. And the first thing we're going to do is look at a little video that I found on the web, and it's related to the concept of normality. So once we look at this video, then we'll come back and we'll kind of make some sense out of it and how random works in this way. And then later in this video, we'll talk about measurement error, and then we'll stop there. And in the next video, we'll talk about how those two things come together to form the basic logic of statistics. And so let me stop here and go and share this little video, which is up on your web page. And so once I get it started, I'm going to blow it up to full screen. And then once it's done, we'll come back and talk about it.
Somewhere in the fields, a brave ecologist is studying wild rabbits. He plans to record the weights of every single rabbit. If he follows this plan, he will notice that most of the rabbits are close to the average, and that there are some rabbits, but not many, that are much larger or much smaller than the average. The further from the average you get, the fewer animals there are. This particular bell-shaped curve is called a normal distribution. Sadly, he has to give up his experiment, for it will cost him a fortune in carrots to complete it. So, he changes the plan. Instead of measuring every rabbit in the whole group, he decides to measure rabbits in small groups, chosen at random from the whole group. He knows that each small group won't necessarily be perfectly representative of the whole group. So he measures many small groups and then compares the averages of each. He starts by weighing 5 rabbits at a time, and he finds that the distribution of the average is somewhat bell-shaped. Then he increases the sample size by weighing 20 rabbits at a time, and then 100 rabbits at a time. Surprisingly, as the sample size increases, the spread decreases. The distributions of average weights becomes more and more normal. What our brave ecologist has just demonstrated is the central limit theorem. The averages of samples have approximately normal distributions. If the sample size increases, this distribution of averages becomes more normal and narrower. What if the population distribution is not normal to begin with? For example, the distribution of dragon wingspan is known to be bimodal. If an even braver ecologist were to study wild dragons and measure dragon wingspans, the distribution of the average wingspan would still be approximately normal. And again, The more dragons our brave ecologist could measure at a time, the closer the distribution of their average wingspans will be to a truly normal distribution. The distribution will also be narrower. So now we know that regardless of a true distribution, the central limit theorem shows that the average of values drawn from the distribution will always be approximately normal. Furthermore, the bigger the sample size, the narrower the distribution of average becomes, and the closer the mean of the sample gets to the true mean of the population. This is why sample size matters so much in any statistical analysis, whether it is a political poll or evaluation of a medical procedure. There is something very special about the normal distribution. Not only do many things we measure in biology follow a normal distribution, but it also crops up when we look at estimates of variables, even when the variables themselves don't have a normal distribution, as we saw with dragon wings. Because of this, we can use the normal distribution to test ideas about the world even when the underlying variables don't follow a normal distribution. My name is Puthikrit Bhattacharya. This video was created by Shui Cho and brought to you by CreatureCast. Special thanks to Casey Dunn. For more stories, visit creaturecast.org.
Okay, let's talk about some of the concepts that were in there. First off, and I'll use some terms here that may or may not resonate with you, but that's okay if they don't. The limits, the practical limits on the distribution of randomly occurring events, and by random we mean that there's nothing influencing those events. It's just how they occur. Sometimes we have what's called a random fluctuation. Sometimes we have systematic fluctuation. We'll talk about that in a minute in terms of error, but the practical limits of normality is 1 to infinity. And we can only truly predict normality at infinity. And obviously that's an unacceptable concept because we can't really have an infinity of occurrences. We can only have at best one infinity minus 1. So at infinity, we have a perfect normal distribution. At less than infinity, a distribution of randomly occurring events might not be normal. In fact, like the dragon wing example, it might be, it might have a couple of modes. It might be, lots of lumps and humps in it. And so we need to think about how do we have a normal distribution that we can use as a predictability factor to be able to predict the probability or the likelihood of a particular outcome. And the other thing that we knew at the time, that had been discovered at the time, that when you randomly pick groups from a distribution, from a random distribution, no matter how skewed it might be or how many lumps and humps there might be in it, that when you look at samples randomly drawn from a distribution, and this is very important, when you look at samples randomly drawn from a distribution of any size, the means of those samples are randomly distributed, and the overall grand mean of all those sample means is equal to the population mean. Now, the benefit of doing samples, which will come into play in a little bit, the benefit of doing samples is that we know that sample means are perfectly normally distributed. And so if we can't do a census of all the possible outcomes of a randomly occurring idea, we can sample a randomly occurring idea out of however many outcomes we have, and those sample means will be normally distributed. Now, obviously, the more perfect distribution would be the narrower one, where we have most everything clustered around the mean and very few below and very few above, but in equal number. And so the larger the sample size, the better representation of a narrow and highly predictable normal distribution we have. For practical purposes in statistics, most of the statistical work we do, we depend upon sample sizes, say of 15 or 20. If you go up to 50, you have much better predictability, much better representation. If you go up to 100, you have better. If you go up to about 500, you have a little bit better. And if you go much above 500, you don't really get you get sort of a diminishing improvement. You don't really get the same level of growth in predictability. And so, sample means above, 400 or 500 are typically not done. And even for these big surveys that they do nationally, they only do 500, 600 maybe, random phone calls or random surveys. And so in practical terms, if you have sample means of 20 or 25 or 30, the distribution of sample means is predictable enough that we can use it to talk about what's the likelihood of a particular sample mean occurring. Now, there's another important concept I've alluded to here, and we keep talking about means, sample means. Statistics is, by its nature, an aggregate process. It's by its nature an aggregate process. And so we don't look at individual outcomes as much as we look at sample means. And so the use of statistical measures means that we're predicting what would happen to groups and not what will happen to individuals. And there's a name for that sort of, if we violate that idea, and it's called the ecological fallacy. It means that you cannot take what you find out about groups and apply it to individuals with any sense of surety or certainty. And so we are looking at aggregate outcomes. And within aggregate outcomes, we know that randomly derived samples the sample means will display tendencies to be normally distributed. And as the sample size gets bigger, the closer it will represent a highly predictable normal distribution. Any normal distribution is predictable, but the bigger the sample means, the more predictable it becomes. So this idea of normality is not one that's a mathematical concept. It's one that's an observable concept, because if you look at anything that's randomly occurs in our world or in our universe, if it's a random occurrence, at some point it begins to display normal tendencies and begins to look normal. So when we say that samples are better than looking at a whole population, that's the reason why. Samples are predictable. The means of samples are predictable. Okay. That's one concept. The other concept that I want to look at, and let's see, is the notion of era. And so I'm going to refer back to a couple of things that I ask you to look at. In fact, I'm going to look at just one of them, because we can use one to kind of represent both. So let me share up this notion of this handout dealing with measurement era that's over on the As You Learn site. So give me a second here. Okay. In looking at the measurement of things, and there's another handout that I would hope that you would look at in this first section that's related to scales and types of variables. Measurement era relates to all of that. It's a little bit more understandable when you're talking about scores, like continuous scale, as we call it, as opposed to categorical scales. But the true score theory, which has been in existence for an awfully long time, says that whenever we look at an outcome, i.e., in this example, X is actually composed of two things. It's composed of the true value of something plus error. And error can be composed of a combination of two things in some proportion. One of those is random error, and that's what I like to call just the cosmic luck of the draw. I mean, you have things that just occur because we cannot measure things perfectly. We cannot define things perfectly. We cannot observe things perfectly. And so there is an element of error in whatever information we collect that is truly just random. And to think about it, let's say we collect the height of everybody that's a student at App State. Well, if we display all those heights, we'll find that they are normally distributed, but we'll also find that people vary according to heights based on a fairly random prediction. I mean, there'll be fewer and fewer people the taller you get, and fewer people the height deprived you get. And so there is a random error component to height. But error can also be systematic. And the systematic part of error, once again looking at height, could be the difference between gender. Gender would be a systematic component that would cause height distributions to vary. And so if we looked at male height distributions, we would probably get an average that's higher than female height distributions. And so the mean of it would be higher for males as opposed to females. Well, the difference in those means is systematic. But within each of those distributions, males and females, there's also the random component having to do with the fact that some people are taller and some people are not as tall. And so anytime we measure something, there's always a possibility and probably and certainly most likely a probability of error in that score. Now, some of that error is random, which would be normally distributed. And so the error would be a normal sort of bell curve around that particular X value. But some of it could be systematic. And sometimes that's the question we ask. Is there a systematic error? Let's say we ask this question: is there a systematic error, or is there a difference between male and female IQs? Now, we know there's a difference in individual IQs, and that's random, but is it also responding to the systematic error that's created by gender, male and female? Now, we can anticipate, because we know that random error will be normally distributed, we can anticipate how big that total error might be. And most statistics is a process of looking at the difference and the relative differences between what we call random error and what we call systematic error. And so statistical processes are not looking at true values, it's looking at the difference in the possible error, because we know that error may exist and we can predict at least the random part of that error. And we can derive what might be the total error. And we'll get into that later, how we do that. Once again, looking at these distributions. And let's say we had, male and female once again. all combined together. Well, we know the distribution of random error is going to be normal. And so whether we have random error or how much random error we have, not whether, but how much random error we have, is also going to be distributed normally. And so it won't affect the mean value, the aggregate value of that particular variable, that particular thing we're measuring. But if we have systematic error, it will affect the mean values. And so we can think maybe we're talking about height once again, and red represents female and blue represents male. Differences in height in average might represent the differences related to purely random error. Well, let me kind of see if I can sum that concept up. And what we'll be doing in the next video, in the next step, we'll be looking at how we use these two pieces together, this notion of normality and randomness, and this notion of random error and systematic error, to begin to build a logic for a system of statistics that allows us to answer questions with a high degree of probability about differences between groups or differences between an individual and a group. Now, so we can not use group data to predict individual outcomes, but we can compare individual outcomes to group data. None of this implies cause and effect. And so when we talk about causation, we're never talking about truly knowing what causes something or what the effect is of something. We're only talking about the likelihood of cause and effect existing. And so when we talk statistics, we're only talking about the likelihood of systematic influences existing. Next step, we'll talk about the modern scientific method. We'll talk about how these two concepts kind of got folded into that modern scientific method. And then we'll do a kind of a preliminary logic set of how we make statistical inference as to whether something is happening or not. Don't get lost yet. Don't give up yet, because this becomes a whole lot clearer once we put it into practice and once we tie these ends together. And so what we've talked about in this video is concepts of normality, concepts of measurement error. And the next video, we'll pull those things together. And so if you have questions about this, when we meet for the first time, gosh, I guess that's 6 o'clock tonight, isn't it? Wednesday night. When I am online first time tonight, we'll kind of talk about these ideas a little bit if you need more explanation. So have a good rest of the afternoon, and hang in there.